You know, I resent the plans to build a nuclear plant nearby, especially with how toxic all that waste is. I'm a very health-conscious person myself, and I would never put a chemical into my body that I don't recognize. The same goes for my kids. The last thing our community needs is nuclear waste in the air and water supply. And especially after watching that HBO series on the Russians, I know how dangerous nuclear energy can be. I never thought this type of thing would happen in my neighborhood. And think of the children. I personally think nuclear energy as a whole should just be banned, and we should focus on more proven, reliable, safer forms of energy, and support our hardworking coal miners, you know? Who's there?
Oh, Ms. Noble, fear-mongering is not a good look for you, especially when you don't understand the complexities of nuclear energy. Allow me to assist.
I think you might have the wrong address.
I have a recurring prepaid cleaning appointment at this address for Mr. Cole Noble?
Oh, Cole's my husband. Well, soon to be ex-husband once the divorce is finalized. And you're clearly not here to clean. Doesn't surprise me that he ordered your services to this house while we were still happily married.
Ma'am, I'm just here to clean, but I don't want to bother you. I'm just gonna head out.
I made excuses for that scumbag for years. All his dirty lies, toxic behavior, and need for space to grow has made this house an awful environment to live and raise children. I bet he's even complained to you about me in his sessions or whatever it is you do.
Yes, but more importantly...
Too bad I'm stuck with him until the paperwork goes through. I think I put this off for so long because I was afraid of being alone.
There are other people besides Cole who will treat you better.
Thanks. Listen, if you've already been paid, why don't you come in and we could chat? I could really use the company right now.
Well, I guess I can't leave you with that attitude.
About living independently from my high school sweetheart for the very first time?
Fuck.
No, you stupid.
Niche.
About nuclear energy. Let's talk about nuclear physics.
Today, we're going to be answering questions of what is nuclear fusion? How does nuclear energy work? And perhaps most importantly, why is everyone, liberals and conservatives alike, afraid of it? Welcome to Bad Astra. Wait, is this being recorded? Let's begin with the basics of nuclear physics. There are two types of processes that can produce nuclear energy. You can have fusion, which combines or fuses atoms to release energy. And you can have the opposite, which is fission. That's when atoms are split apart to release energy. Now, if every atom was capable of doing both, it would literally break physics. Conservation of energy is important if you want a stable universe. Let's talk about size. It matters. But every size has its benefits, and with a few adjustments, it'll work just fine. For this video, an atom's size means its atomic weight, or its total number of protons and neutrons together. Generally, elements with more protons require more neutrons to keep all of the protons glued together. So, generally, but not always, elements with more protons have bigger atoms. Smaller elements, with fewer total protons and neutrons, like hydrogen and helium, can fuse into larger elements to release energy. But, as we learned in our previous video, larger elements release less and less energy in fusion reactions. The biggest element that still gives off energy in its creation is iron. And that reaction mostly happens in the cores of giant stars because it requires a lot more energy than the smaller element fusion. Even blue giants have to work their way up and ease into those iron fusions. In this case, smaller is better if you want the most efficient energy results. Even though the larger, more complex atoms might seem cooler, bigger isn't always better. In fact, the fusion creation of elements with more protons than iron is too big, and very painful, even for the biggest of stars.
You would think that bigger atoms would be ideal for these sorts of reactions, because video games have taught us that the greater the difficulty, the greater the reward.
But in cores of stars, the opposite is true. Higher element fusion releases less energy than lower element fusion, and fusion reactions past iron become endothermic, meaning they absorb energy.
We've all had particularly exhausting fusion encounters, right, Sharon? We put in all of this energy and care, but we can't always get the energy release we want. Sometimes a relationship just isn't worth the effort.
Listen, I can understand the parallels you're making here, but I can assure you, I just want you out of my house.
Not before you learn about nuclear physics. Where was I? Right. You can't always get what you want. Unless you're the universe, and get to set the laws of physics.
Like Honey Badger, the universe just takes what it wants. Well, it's an unfeeling void and therefore has no conscious wants or desires. Unfortunately, God did not return our requests for comment. And Nietzsche, who killed God, also did not return our requests for comment. Because...
Dead, Jim.
But how does this fusion happen? How does it produce energy?
Well, when two atoms love each other very much... Actually, Sharon, you might want to cover your ears for this part.
I have 2 kids. I understand how the diddly-doing works.
The what? Well, good news. We've gone over this in a previous video. Flashback time!
Nuclear fusion occurs when two atoms, usually hydrogen atoms, really just protons, collide with each other and get very lucky. Increasing the temperature makes protons move faster, and gravity confines them in a tight space to increase the likelihood of collisions. And when gravity gets a bunch of hot, sweaty protons moving around in a confined space, you're going to get collisions. With enough collisions, some of those protons are bound to discover a spark and collide with just the right conditions to merge into one, combining an exquisite release of energy, powerful enough to light up the sun. The energy released from these fusion reactions heat up the surrounding protons, causing more collisions and more fusion events.
Now, the real process is a bit more complicated and involves neutrons, but that's a little too kinky to go into in this video.
But not too kinky for this one. Let's talk about quantum tunneling.
So you have your hydrogen in the star that is ionized, which means that the electrons and protons are separate. The protons are really the only relevant part for this conversation. Protons are positively charged, so they repel each other, like when 2 of the same sides on a magnet get pushed together, or a pair of X's that really hate each other and can't be in the same room at the same time. That repulsion is called the Coulomb barrier, probably named after some scientist with that last name. To fuse, the protons have to be moving super fast towards each other so that the slowing force of their charges doesn't stop them from colliding. Then, these protons need to get over whatever old drama they went through, get really close together, and then get bound together with the strong force, which isn't just any strong force. The strong force is the force that binds an atomic nucleus together.
As the name implies, it's strong, because scientists shouldn't be allowed to name things. Like the ELT, or Extremely Large Telescope. The OLT, or Overwhelmingly Large Telescope, was deemed too ambitious and didn't get funding though.
To activate the strong force, the repulsive, slowing Coulomb barrier must be overcome, which requires a lot of kinetic energy. In the core of a star, the high heat and pressure means that protons have a lot of kinetic energy when bumping into each other. Yet none of that energy can even come close to overcoming the Coulomb barrier, so the protons should never collide.
So, the strong force can never take over and the fusion doesn't happen? But that makes no sense. In the video you just had me watch, we learned that fusion powers stars. And stars exist, So,
Exactly. It makes no logical sense. And whenever small things are making no logical sense, you just know your messy drunk friend quantum mechanics is involved.
The quantum scale is only relevant to super itty-bitty things you would need a scanning electron microscope to see. But that includes protons, so buckle up.
Think of quantum tunneling like a cheat code of the universe.
And Heisenberg gets involved. No, not the brilliant blue math chemistry teacher. The brilliant German physicist who led the Nazi nuclear weapons program. But before he was a Nazi, or secretly sabotaging Nazi Germany's attempt to build nukes, historians have a range of headcanons on that one. Back in 1927, he came up with Heisenberg's uncertainty principle. This principle states that the uncertainty of a particle's position is inversely proportional to the uncertainty of its momentum. So, if we know exactly how fast something's moving, we have no idea where it is, and vice versa.
And by we, he didn't mean human scientists. He meant the universe itself has no idea, even though, again, it is an unconscious void that has no thoughts. If this seems absolutely insane to you, you're not alone.
Even Einstein got pissed off by this and was all like, God does not play dice with the universe. But observations support Heisenberg on this one.
So, I guess even the universe likes to gamble on the little things.
God did not return our request for comment, nor did Nietzsche. Back to the cheat codes. Heisenberg tells us that even after pressing up, down, left, right, BA, you can't know the exact location and speed of a particle. However, you can figure out the relative probability of where this particle is and how fast it's moving, which is represented by the wave function. And the most logical place for the particle to be is also the most likely. With wave functions, we can tell that the proton is most likely outside the Coulomb barrier of the neighboring proton. That's the power of math.
Juliet is up on her balcony. Romeo's down below.
oh, I recognize this metaphor. So, does quantum mechanics give Romeo the energy he needs to climb up on the balcony and do the do with Juliet?
Nope, it's weirder. The proton doesn't have enough energy to overcome the Coulomb barrier. Romeo's a weak little...
So fusion doesn't happen?
It's even weirder.
Remember that this wave function just tells us where Romeo is most likely to be. But sometimes, our Romeo proton just pops up behind the Coulomb barrier. He found a tunnel that shouldn't exist and walked right through. The universe thought Romeo was most likely outside.
But actually, he's now inside the Capulet house and fusing with Juliet as we speak.
How? That makes no sense.
Yeah, that's what pissed off Einstein. Apparently, the universe is not just cold and unfeeling. It can't be bothered to pay attention to the little things. So, we use quantum mechanics to understand super tiny stuff that doesn't follow our normal math.
And frankly, we don't deserve any explanation for the activity of protons bumping. That's their business. I've heard that before.
Okay, so now we've used our tunneling cheat code. The two protons have combined and are bound together by the strong force.
And that's it, right? We're done with the fusion reaction and you can untie me?
Not even close. Next, one of the protons becomes a neutron because, surprise, one of the protons is fluid and feels like a neutron today, which, of course, the universe respects, as it provided the conditions to allow this to happen.
But a proton can't just wake up one day and decide it's something that it's not.
Shut up, Sharon. Your bigoted views on how particles identify is problematic on every scale, including the quantum.
So we have a proton and a neutron that form deuterium, which is a fancy way of saying hydrogen with a neutron. Then another proton joins in, also through the tunneling cheat code, because threesomes always sound more fun, until they're not. All of a sudden, the neutron is overwhelmed with the needs of two protons and the whole thing becomes unstable. This unstable three-way is called helium-3 because it has two protons, making it helium, and three combined protons and neutrons, giving it an atomic weight of 3 atomic mass units. Just as the toxic relationship is losing hope of happiness, another helium-3 enters the room, And the two triads get to tunneling and talking and realize that they're both unhappy, but might see something in each other.
And after a soul-bearing conversation, one particle finally says, "Listen, we've gotten a bit over our heads. Yeah, this sounded like a fun idea, but there's no shame in admitting that disappointing everyone is worse than ending things. Two of our protons are regretting getting involved with us in the first place. How about we let them go, no hard feelings, and combine to be a simple, stable foursome?"
Relieved that someone finally suggested it, the threesomes combine and the two unhappy protons leave. The remaining two protons and two neutrons become a stable helium foursome. Fusion is a much better experience when everyone's needs are met and communication is open.
This all just seems blasphemous.
Listen, you might be subscribed to monogamy, but that's just not how the universe works.
Polytriads are the natural order of things.
But you just said threesomes don't work out.
Because that's helium and foursomes work better for them. Carbon prefers threesomes. Every element has different needs, and we should respect that.
Okay, so what does this have to do with energy?
Right. So when the proton and neutron decided to spice things up and invite another proton to the party, the combination released a gamma ray, which is light energy. Back when the two protons initially came together, before one turned into a neutron, a positron and a neutrino were released. The neutrino is asexual and has no interest in any of this. Except sometimes it suddenly changes flavors into a different type of neutrino because space is vast and the void gives you a lot of room for self-exploration. The positron goes off to find an electron and they completely annihilate each other, producing more gamma rays.
Is this annihilation another lewd act?
Nope, just straight up murder-suicide and poof from existence. Oh, so let's talk about when an atom has decided fusion isn't working out and wants a divorce.
Finally, relatable content.
Fission happens with heavier elements that get split, violently. This happens naturally with heavier, unstable elements as they decay. Quick chemistry refresher. Elements are differentiated based on their number of protons, which is why each element on the periodic table has a number. That's the number of protons it has. Easy, right? Well, it gets a bit more complicated when you start talking about isotopes. Different isotopes of an element have the same number of protons, but not the same number of neutrons, so things are a bit different. The atomic weight of an element is the protons plus the neutrons, and the elemental identity just depends on the protons. So one element can have several different atomic weights, or isotopes, which can have varying degrees of stability. For example, uranium's atomic number is 92, because it has 92 protons. On Earth, most of the uranium we find has 146 neutrons, for a total atomic weight of 238. This is the more stable uranium isotope, and we call it uranium-238, because scientists are very creative. However, some uranium only has 143 neutrons, bringing the atomic weight down to 235, and dramatically decreasing its stability. This isotope is called uranium-235, despite Dr. Strangelove's more descriptive submission of Teeny Magic Boom Boom.
Think of different isotopes like the brand name and off-brand version of elements. Not unrelated, but definitely a little different.
Aren't electrons a thing too?
Yes, electrons exist and are important. Well done, Miss Noble. You remembered something from high school chemistry. However, nuclear physics is physics just dealing with an atom's nucleus, so the electrons don't matter right now. What matters in isotopes is the neutrons, because they have an impact on how the atom functions.
They're like mood stabilizers, so the fewer neutrons you have, the more unstable the isotope.
That's a generalization, and too many neutrons can overcorrect and also cause instability. That is why you should always take your prescribed dose of medication unless your doctor tells you otherwise.
Warning: too many neutrons may cause atomic weight gain, instability, decay, and other effects determined by further study. Do not take under doctor's supervision, as nuclear physicists increase your risk of criticality and explosions.
Let's start discussing the decay of unstable isotopes.
Each isotope of an element has a different level of stability, and you would think that determines the exact time of decay.
Joke's on you, because the universe still loves to play dice in this matter. And the timing of a single unstable atom's decay is spontaneous, and we can only know the probability, or about when the atom will decay. However, since we know the probability of one atom, we can figure out how percentages of material will act over time with
Power of math.
just as we're not sure how one coin toss will end up, but if we toss the coin a few 100,000 times, we know we'll get heads about half the time. You've probably heard of a half-life.
This refers to the amount of time it takes for roughly half of an isotope's material to spontaneously decay. So after 2 half-lives, only half of a half, or 1/4 of the original material is left. After 3 half-lives, 1/8. This is one of the only times fractions actually comes in handy to explain things.
How is any of this useful? Besides knowing that shorter half-lives are when you should GTFO to avoid radiation poisoning?
GTFO?
When you should run, Sharon. Run very fast away from the radioactive material.
Anyway, half-lives are how carbon dating works. The half-life of carbon-14, so carbon that has 6 protons and 8 neutrons, is 5,730 years. If you have a thing, and you know how much carbon-14 it should have had at the beginning of its existence, and how much carbon-14 it currently has, you can figure out how old the thing is. You're welcome, paleontologists.
Thanks, physics.
However, it is possible for fission to go off the rails, completely abandon all civility, and just destroy an entire city.
This process is referred to as runaway fission. It's when fission reactions cause more fission at a faster rate in a chain reaction that can't stop and releases an incredible amount of energy. An atom that undergoes fission, or breaks apart and releases energy when hit by a slow-moving neutron, is referred to as fissile, the adjective version of the noun fission. In runaway fission, a random neutron collides with one fissile atom, causing that atom to break apart, which releases more neutrons. Those neutrons then collide with other fissile atoms. They break apart and release more neutrons that collide with more atoms that split and release more neutrons that collide with more atoms, and then...
This chain reaction always happens when you get enough atoms of a fissile isotope in one place.
This amount, or critical mass, is like a giant stick of dynamite. Any passing neutron will light the fuse, set off the chain reaction, and cross the point of no return for runaway fission. You get a big chunk of the good stuff, and boom. Divorces are being filed and finalized in record time, and none of them get back together. If you use neutron reflectors, this critical mass can be smaller, because the neutrons that normally would have left that explosive situation are forced back into the drama and can break apart even more atoms.
Well, maybe these neutrons shouldn't get involved in other people's marriages and make the situation worse, Carol.
I'm Astra?
I never thought we had communication issues. And then the lies and the gossip. The entire PTA board knew about it.
All right. I suppose now would be a good time to hear from our sponsor. Science, Tommy.
Trust me, I have got an associate's degree, and don't you worry about it. It's Science Time, and I am back. The world's first human-made, self-sustaining nuclear chain reaction happened inside a pile of graphite bricks in the city of Chicago. This reactor was creatively named Chicago Pile 1. Someone at some point decided maybe cutting-edge experimental nuclear research shouldn't be done in the middle of a large city, so Chicago Pile 1 was deconstructed, moved to what was then called the Argonne Forest, and reconstructed as Chicago Pile 2. The desire for more piles, among other things, led to the Argonne National Laboratory as it stands today, an outstanding facility whose research has aided in the development of nearly every commercial nuclear reactor in operation today. I was able to take a tour of the facility, so of course you know what the rest of this video will be about. Mirrors. On cars, the passenger side mirror always says objects in the mirror are closer than they appear. But why? Why are the objects closer, and why is it just the passenger side, not the driver's? Well, we're going to learn today. I forgot to film this part in the studio, but I'm Science Tommy, and as the name implies, my full name is Science Thomas. So why are objects closer than they appear? Well, if you roll up a $20 bill, you can smell why. The passenger mirror is convex, meaning it bulges outward, compared to the driver's side, which is perfectly flat. Not to be confused with concave, like this mirror here, which bends inward. A good memory technique is to think of concave mirrors like actual caves, because they go inward. Being convex gives the mirror a wider field of view. Notice how both of these mirrors are the same distance away from me, but in the passenger mirror on the left, you see more of me. Also, notice how I look smaller. As objects get farther away from our eye, they appear smaller, and vice versa. So passenger mirrors are labeled like that because they shrink the image they reflect, and human brains just assume things that look small are far away. So in conclusion, Sharon, it's not small, you're just far away.
I've heard that before. More importantly, you've pulled yourself together. And now we can talk about the applications of nuclear energy, specifically for fission.
Is there a safe word to stop all of this?
Of course there is. However, as I learned from my fiance, there's no safe word with the power to stop an excited physics lecture.
For nuclear fission to be effectively harnessed for energy, we have two main material options here on Earth: plutonium and uranium. The uranium we have on Earth is 99% 3 U-238, which is incredibly boring and has a half-life around the age of the Earth, the real age of 4.5 billion years. The other 0.7% is U-235, which is the good stuff. U-235 goes through fission and releases energy when hit by a slow-moving neutron, which makes it fissile.
About 0.005% is uranium-234, but
She doesn't even go here.
U-238 isn't completely useless, but in order for it to turn into something usable, it needs a strong dose of neutrons. U-238 can capture a neutron and become U-239, then become Neptunium-239 when one fluid neutron becomes a proton, and finally Plutonium-239 when a second fluid neutron becomes a proton. This Plutonium-239 is fissile.
through neutron capture and particle fluid identities, the rotting corpse of U-238 suddenly becomes useful, like Frankenstein's monster. Although this repurposing ends significantly better for scientists today. So let's talk about plutonium.
What about Pluto?
No, plutonium the element, not the dwarf planet.
You mean planet.
Not in this video, Eris. Anyway, plutonium is the element with the highest atomic number to naturally occur on Earth. But it's only found in decaying uranium-238 and typically only in trace amounts. So, if you can't find locally grown plutonium, store-bought is fine. You just want to make sure that the plutonium you make is 239 or 241, because both are super fun and fissile. If you end up with plutonium-240, you might as well cancel the party, because plutonium-240 will judge you for your kinks and make the entire reaction less fun because they refuse to loosen up a bit and will continue to judge you for taking a bath, even though that's the most normal part of the party. If you can't handle me taking a bath, then you don't deserve me at my most reactive state.
So, what do you need to harness all of this energy? First, you need unstable elements. Doesn't matter the flavor as long as it's fissile. Then, you need a critical mass of the stuff, separated into two chunks that you can combine when you're ready. Achieving a critical mass is the hard part, because the fissile stuff is hard to come by.
That's why you hear about enriching uranium.
Oh, like the Iranians are doing for bombs.
That is a complicated political matter that has very little to do with physics and involves more countries than just Iran. Bombs are not the only use for enriched uranium because it takes a lot more refining to get it to weapons grade, but we'll get into that later. Enriching uranium is the process of separating U-235 from the boring U-238 that doesn't react. The process uses a centrifuge, which spins things around really fast until the lighter stuff rises to the top and the heavier stuff sinks to the bottom.
A higher purity of U-235 requires less total uranium to get to a critical mass for runaway fission.
Next, you need questionable ethics and a moment to ask yourself, is this really what I should be doing? Why don't I make something more pleasant, like pretzels or cake?
Finally, you need to combine your 2 chunks of purified fissile material into a critical mass and wait a split second for a stray neutron minding its own business to be in the right place at the right time. This passing neutron will collide with one of the atoms and set off the unstoppable chain fission reaction. Boom. Literally. All you need is a critical mass of enriched fissile material, a method of delivery, either a remote way to combine the material or a death wish, and you have an unimaginably evil and powerful bomb.
Oh, we're on bombs again?
Yes,
I thought there were other applications.
there are.
Why are we talking about bombs then, if it can also be used for energy?
Because humanity thought of weaponizing fission reactions to level cities before we considered making clean energy to power them.
Why did we do that?
Because we were in the middle of a war and humanity is inherently destructive? What? Sorry, we've wandered into history and philosophy, and that's not my area. Eris!
How does one make a Manhattan? 3 ounce. Didn't fill this up otherwise, so we're just gonna. So I'm a little concerned of how this is gonna taste. But I'm not one to say no to alcohol. And what's a dash? Something to stir it with. I'm just gonna stir it like I am a professional bartender. That looks like alcohol. Hi, I'm Eris, the writer for Bad Astra, and apparently I'm in charge of this portion of the video because Astra thinks that all liberal arts degrees are the same. So, in order to keep this fun and on brand, I've made the horrible decision to take a shot every time I say the word bomb. And there are at least 7 times in my written script where I do say the word bomb, which might kill me as a very tiny person whose tolerance isn't nearly as high as it was at the beginning of quarantine. So, if you would like to join me, I encourage you to take shots of water, because at least then you'll be taking care of your health instead of almost getting alcohol poisoning. Let's have fun until I bring down the mood about literal war crimes. 1939. A ton of scientists in the US, most of which were refugees from Europe, came to the US government and they were like, hey, have you considered the military applications of nuclear fission? And the US government was like, we haven't. Can we give you money to do the thing? So in 1940, they received $6,000 to start their research into nuclear fission being a weapon. It transferred to another government agency in 1941. Point is, everything got serious when we discovered that the Nazis were trying to do the same thing. They were like, fuck, we have to beat the Nazis to figure out how to create a nuclear bomb. All right. Initially, they were trying to separate U-235 from U-238 in order to get enough fissile stuff to work with. But they realized that they couldn't separate it using chemicals, and they had to separate it physically. So UC Berkeley was like, hey, we figured out that we can use electromagnetism in order to separate the two. And Columbia was like, cool, that's awesome. We figured out a way how to separate them using diffusion. So that's neat. Basically, both of those sucked because it required a lot of time, it required huge facilities, and it required a massive amount of electricity to actually do the thing. But then a guy named Philip Haig Alderson, which I think is how you pronounce it, I'm not too sure, he was like, wait guys, I know how to do this, but with thermal energy. While they were all trying to figure out how they were going to get enough of the fissile in order to make an actual bomb, I did this to myself. But while they were trying to figure out how to get enough fissile material, they also had to figure out how they were going to transfer that fissile material without setting off a reaction while it was on a plane. Because, spoiler alert, if you get a supercritical mass of fissile stuff, like we discussed earlier, so there was a lot of research that had to go into that, especially while they were waiting on the fissile stuff so they could actually test. So J. Robert Oppenheimer was the one who was in charge of this entire plan, and his research was happening in Los Alamos, New Mexico. And that's the area that people typically refer to when they're talking about the Manhattan Project research. They're talking about New Mexico, which Manhattan is not in. The reason why it's called the Manhattan Project in the first place is because Columbia University did a lot of the research initially that led them to the production of all of this stuff that shall not be named. Not because all of them were getting based on Manhattans to deal with the moral implications of what they were doing. That's what I'm doing. If the Manhattan TV show is to be believed, their families didn't know why they were out in the middle of the desert. They only knew that World War II was happening and the military was moving them out there, and their significant other or whoever was in their life that moved them out there was doing the science thing. I would take that with a grain of salt because the Manhattan TV show did take a lot of creative liberties, including the addition of Paul Crosley, who was not a real scientist who worked on the Manhattan Project, and honestly was probably just a clever excuse to get Harry Lloyd on screen. And speaking as someone who's been madly in love with that man since the age of 12, I totally understand why they did that. Thirst for Harry Lloyd aside. Summer of 1945. They finally had enough of the fissile to start testing in the flavor of plutonium-239. At this point, the total budget had gone up from $6,000 originally to $2 billion, which, speaking as a poor millennial, is not a number I can even begin to comprehend in terms of money. And then you add inflation on top of that, and when you adjust it, it's bigger numbers that I didn't take the time to look up. On July 16th, 1945, at 3:30 in the morning, at the Trinity test site in Alamogordo, New Mexico. Alamogordo? At the Trinity site in Alamogordo. Alamogordo. Of course, they needed to test the bomb. I'm gonna die. The test for the first nuclear weapon was dropped in front of scientists and dignitaries who were watching from 10,000 yards away. Fireball. Sonic boom. Maybe that happened. I don't know. I'm just embellishing at this point. But a 40,000 foot tall mushroom cloud, because we're in America and we don't use the metric system. The tower that they used to detonate it from completely vaporized. The desert, 800-yard radius of pure glass. Here's where things get dark and serious. When you develop such a powerful piece of technology, a weapon, do you look at what it did and go, hey, that was a lot of fun, guys. Really appreciated being in the desert with you, but let's pack it in and never talk about this again and not use it. Done. Or do you look at it and go, wow, that was a lot more destructive than we anticipated. All of our fancy equipment is completely vaporized. How about we try using nuclear fission on energy instead? Because that'll be more productive for humanity as a whole instead of weapons. Or do you take this technology that you developed and drop it on two populations that had a lot of civilians in it over the course of 2 days? Well, if you're America, you'll choose the last option. And after Canada and the UK signed off on it because they were helping us develop the technology, we dropped 2 nuclear bombs on Japan. On August 6th, 1945, America dropped the first nuclear bomb on Hiroshima. It killed 70,000 people from the initial blast and from the events shortly thereafter. On August 9th, 1945, Nagasaki became the second city that America dropped a nuclear bomb on. It killed 40,000 people from the blast. These, of course, are just estimates as to what happened. Because, believe it or not, dropping a nuclear bomb on a city completely vaporizes records and prevents us from really figuring out the exact numbers. And those death counts have only increased as a result of the effects of nuclear radiation poisoning. I'm talking about destroyed central nervous systems, autoimmune diseases, and a lot of cancer. I've seen some estimates that go as high as 200,000 people. That's a lot. If you grew up in the American education system like I did, you probably heard a lot of justifications for what we did. I know I was fed the story of, Japan was not going to surrender unless we dropped those 2 bombs. And when you consider how much longer the war could have lasted, we probably saved more lives by dropping those 2 bombs than what could have been lost if the war continued on into November. You hear arguments that are like, well, how are you going to have a weapon that could end the war and not use it to end the war? It's a complicated moral topic, and honestly, what I've done is simplified it a lot. But the one question that I have always asked is, couldn't we have found another way? Was there really no option other than dropping 2 nuclear bombs on our enemies? Something that has been banned afterwards because of how destructive it was. I always think that the least amount of harm should be done. And I look at those 2 bombs as an American and I go, there should have been another way. How do we look at those 200,000 lives and say that was a worthy sacrifice for peace? But that's speaking from someone who is looking at it from a modern perspective and someone who has not studied this in depth. My grapplings with the topic aside, there is a real historical debate as to whether or not those bombs should have been dropped. Some people point to the Japanese peace negotiations with the USSR that were happening before the bombs were dropped. And there are some people who point to a document that shows US projections saying that the war would have ended in November because that's when the Japanese would have surrendered. However, there is an argument that the USSR during World War II under Stalin was not going to seriously negotiate a surrender, and those talks couldn't have been genuine. There's also an argument that pointing to that US projection is not completely accurate, and giving it a modern historical reading is very different than reading it in the context of the time. In the middle of a world war, nuclear historians Alex Wallerstein and Michael Gordon have also pointed to documents that say we were going to drop multiple bombs on Japan. So the question of why did we drop 2 bombs really should be, why did we stop at 2? This is a very complex issue and a very complex topic. I do still have a lot of questions. What other avenues could we have explored and exhausted before dropping those 2 bombs? Could we have negotiated a conditional surrender with Japan instead of demanding an unconditional surrender? Could we have found other ways of fighting them that didn't involve dropping a nuclear bomb on large populations that included civilians? Why couldn't we have found another way? There should have been another way. But hey, that's just my 2 cents. I have an English degree, so I don't understand the complexities of the historical context and the moral and ethical arguments, so I highly encourage you to do your own research because this was a very simplified version of a very complex issue. Also, the fallout of it and the primary documents in terms of conversations that Oppenheimer had were incredibly fascinating, but I just didn't have the time to put them in here. I'm gonna go recover from the bad choices that I've made in the making of this video. Maybe I'll figure out who to drunk text today. Back to you, Eris. That's me. Back to you, Astra.
Wait, we committed atrocities against civilians and children? But no, we're America. We're the good guys.
Oh, you sweet summer child. Anyway, let's focus on the more productive and wholesome application of nuclear fission, which is nuclear energy.
I have to disagree.
You really want to disagree and say nuclear energy is worse than nuclear bombs that vaporize people in seconds? Is that really the hill you want to die on? Before we debate the ethics of nuclear energy, let's get a clear picture of what nuclear energy is.
You probably already know what a plant looks like from the outside, but let's discuss the inside. There are three main parts of a nuclear reactor: the fuel rods, your enriched uranium in ceramic pellets inside metal tubes, the control rods, neutron absorbers like lead, and water, your coolant and moderator. The water both prevents overheating and speeds up the nuclear reaction by slowing down the neutrons bouncing around the tank.
Slowing the neutrons down actually speeds up and sustains the chain reaction, because slow neutrons are more likely to bump into a uranium-235 atom.
Remember, the nuclear chain reaction is perpetuated by neutrons from previous fission events crashing into and splitting new atoms.
Those neutron homewreckers sound pretty bitter. Just because their marriages fell apart doesn't mean they have to go around disrupting other happy couples.
Pretty much. And the amount of homewreckers involved affects the rate of fission.
If you want to speed up this chain reaction, pull some control rods out, so fewer bitter neutrons are absorbed and more are bouncing around splitting atoms. If you want to slow down the reaction, add more control rods, which absorb neutrons before they can get to the next uranium atom.
Oh, so the lead control rods are like neutron therapists, and the water moderator is that friend who's egging them on and trying to start drama.
I totally am that friend.
But still, if you take away all the therapists, all the newly divorced neutrons will have no positive coping mechanism and take out their anger by splitting up other atoms.
Exactly. By adding or removing the therapist control rods, operators can control the speed of the chain reaction.
But aren't the newly divorced neutrons unpredictable? How do you know which direction they'll fly off in and where to put the neutron-absorbing control rods?
Even though we have no idea how each individual neutron will behave, there are countless atoms and neutrons involved. So scientists can predict pretty accurately how the neutrons will all behave collectively.
Just like half-lives.
Exactly.
Anyways, these divorces release energy in the form of heat, which heats the water and turns it into steam. From here, the process is just like a coal plant. The steam spins a turbine, powering an electric generator.
So if we're comparing to a coal plant, the fuel rods are the coal, the neutrons are the fire, and the control rods are the water to splash on the fire if it gets out of hand. The water is both kerosene to speed the fire and the water being heated into steam.
Sharon, that is correct. I'm impressed.
I voted for Bloomberg in the primary.
And it's gone.
But what if something goes wrong and the fuel rods get too close together? They could form a critical mass and turn my nice suburban home into the next Hiroshima.
I see where you're coming from, but that's not really possible because of the uranium's purity.
Nuclear energy only requires reactor-grade uranium and plutonium, which is way different from weapons-grade. In most commercial nuclear reactors, the uranium used is 3 to 5% U-235, which is the good fissile stuff. Research reactors are usually around 12 to 20% because academics are just that bougie.
Also in research, contaminants are an issue, but academics are still bougie.
Weapons-grade uranium usually contains around 85% U-235.
And scientists once purified up to 95% U-235 in an RV just outside of Los Alamos.
With plutonium, as long as that buzzkill P240 is under 7%, the stuff's weapons grade. Reactors need more of a vibe killer because we don't want reactors blowing up, so 7 to 19% buzzkill is called fuel grade, and plutonium that's more than 19% P240 is reactor grade.
Normally, I like explosions. But when we're talking nuclear explosions, I'm gonna pass. Radiation burns aren't good for the skin.
So you could never get a critical mass and blow up the nuclear reactor.
No, reactors do not blow up in the nuclear bomb sense.
In an extreme meltdown scenario, you can superheat your cooling water, which immediately vaporizes and causes a steam explosion.
That's very bad because it can expose your reactor core and spread fuel around. But it doesn't release anything close to nuclear bomb levels of energy.
And it can be contained if you have a containment dome over your reactor.
That's why there's a difference in purity. Less pure uranium and plutonium is used in reactors so they don't blow up. And it's way cheaper to make lower purity material. These impurities mean the worst a reactor can do is melt down. Granted, that's still terrible and kills a lot of people, but it's not close to the levels of an atom bomb.
But what about Chernobyl and 3 Mile Island? I still remember hearing about it on the news. And that HBO series showed just how horrible radiation poisoning can be. Didn't you see how all those people died such horrific deaths? What if that kind of thing happens here?
Okay, relax. This is a fair point. Disasters like Chernobyl, Fukushima, and 3 Mile Island have happened and were horrible.
However, all of those disasters were avoidable and are very different from anything that would likely happen in 2020 in America.
But aren't we the bad guys all of a sudden?
Firstly, yes. Secondly, it's not all of a sudden. Thirdly, the reason why it wouldn't happen here in the same way as Chernobyl is that even back in the 80s, we had much stricter regulations on power plants. And those regulations have gotten even stricter as we've learned more about nuclear energy. What happened to Chernobyl was a masterclass in cutting costs and being stupid. Everything that could go wrong did go wrong, and no one communicated effectively with each other or the public.
They didn't have a containment dome, idiot cheapskates. They used cheap graphite-tipped control rods, which actually accelerated the fission reaction they were trying to stop, idiot cheapskates. Performed their test outside given procedures and with untrained staff.
Why would you even then suppressed information, which is how the USSR rolled, baby. As a result, tens or hundreds of thousands of people may have died, but we'll never know exact numbers. I encourage everyone to check out the HBO miniseries. It's artistically incredible, and they didn't shy away from the science.
So the Russians are the bad guys again.
Where do you get your news? Anyways, this time, because of lax regulations, unrealistic timelines, and government-controlled press, yes.
And we're the good guys again?
No, life isn't black and white when it comes to morality, Sharon. This good guy versus bad guy narrative is a false dichotomy completely dependent on which perspective you're looking from. Besides, we're both the bad guys.
What? Okay, but what about Fukushima? Are you going to say Japan was also stupid?
Fukushima was more a case of really bad luck and less than stellar plant location.
On March 11th, 2011, a giant earthquake and tsunami caused 3 meltdowns in the Fukushima plant. This event had a single cancer death attributed to the resulting radiation exposure, and indirectly caused 1,600 stress-related deaths due to the hardships faced by people evacuated from the affected area. That's around the same number of fatalities which were directly caused by that tsunami.
The lesson we can learn from this is to not put reactors on fault lines or coastlines, which is geographically difficult for Japan, but completely doable in the United States. For example, my home state of Illinois has 11 nuclear power plants operating at 6 sites and could use a few more.
But aren't we in Central Oregon?
There's a pandemic, Sharon.
Okay, but 3 Mile Island was in the US. Are you going to say Pennsylvania is a dangerous place to put a plant?
Only in Philly after a police shooting or an Eagles Super Bowl win.
Yes, 3 Mile Island happened in the US, but comparing it to Chernobyl or Fukushima is misleading.
Why? They're all nuclear meltdowns.
But not on the same scale.
While Chernobyl and Fukushima were both level 7, or major accidents, 3 Mile Island was only a level 5, or accident with wider consequences.
The partial meltdown of 1979 was caused by a system malfunction, and reports from the World Nuclear Association and Columbia University found no deaths, injuries, or adverse health effects caused by the accident. The radiation released was hazardous to the people inside the facility, but not to the general public. 2 million people were exposed to radiation from the incident, but only about as much as you'd get from a single chest X-ray. Even in the worst nuclear reactor accident the US has ever had, the government regulations protected everyone. And when we compare to the environmental damage of coal mining accidents, fracking, or oil pipelines leaking or bursting, well-regulated nuclear energy is way better, even when accidents do happen.
Okay, so catastrophic accidents can be mitigated with better plant design. But what about long-term effects? I heard that nuclear waste drips into the water supply and poisons the earth after it's done with this fission nonsense. So how do you explain that, Miss False Dichotomy?
Yes, nuclear waste is very dangerous if not stored properly. Ha! However, let's compare it to our current main sources of energy, natural gas and coal. The use of nuclear energy doesn't emit any carbon dioxide into the atmosphere. Fossil fuels, however, release the greenhouse gases that have destroyed our atmosphere and caused climate change. In fact, even accounting for those 3 major disasters and all other deaths related to accidents and long-term damage from nuclear plants, nuclear power is estimated by NASA to have prevented 1.8 million net deaths worldwide between 1971 and 2009. It also prevented 64 gigatons of CO2 equivalent greenhouse gas emissions globally. Air pollution, mining accidents, and natural disasters caused by climate change kill a lot of people.
But isn't nuclear waste worse than CO2?
In comparable quantities, yes. But let's talk amounts, shall we?
Nuclear energy produces 9 grams of CO2 equivalent per kilowatt hour from building the plants, mining, enriching, and transporting the material. Compare that to an estimate of between 790 and 1,017 grams per kilowatt hour for coal. Let's be conservative and take a low end of that estimate, saying that coal produces around 800 more grams of CO2 per kilowatt hour. A conventional nuclear reactor produces 0.0015 grams of waste per kilowatt hour. That's a frankly minuscule amount compared to the greenhouse gas emissions you're saving.
Unless you want to argue that nuclear waste is over 5 million times worse than CO2, fossil fuels are way worse.
But what if I do believe that nuclear waste could be 5 million times worse than CO2? You're comparing apples to radioactive oranges. And the field of applied nuclear physics hasn't even been around long enough to know the long-term impacts of nuclear energy for certain.
Okay, for the sake of argument, sure. We don't really know the long-term impacts of nuclear waste, but we do know how to mitigate them. In addition to nuclear plants producing far less waste, storage of that waste is highly regulated to prevent exposure to the public and pollution.
Spent fuel rods are stored underwater for 5 years, then put in dry storage, which basically means encased in a buttload of concrete. The ultimate location of this waste should be deep geological storage. Basically, bury it under a mountain in a dry area.
So we just take our problems and bury them under a mountain?
It's actually way more effective than it sounds. 250 to 1,000 meters of rock blocks most of the radiation. And I noticed that you haven't complained much about the frequent oil pipeline leaks and fracking that currently wreak far more havoc on the environment than nuclear waste storage. It isn't perfect by any stretch, but nuclear waste is far better for the planet than fossil fuels.
Okay, so nuclear energy is better for the planet overall. But I'd rather not live near a center of radioactivity. Not in my backyard. Forget the overall impact on the planet. What about my neighborhood?
So you specifically want less radiation getting into the local environment from power plants?
Of course.
So you support switching from coal plants to nuclear energy?
Since the fly ash emitted by coal power plants, a byproduct from burning coal for electricity, carries into the surrounding environment 100 times more radiation than a nuclear power plant producing the same amount of energy.
Okay, I'm gonna need a source for that statistic because that doesn't match anything I've heard.
Oh, the Scientific American article I quoted is linked up in the cards. And yes, I did confirm with several sources. By the way, all the sources for this video are included at a link in the description.
God. Coal releases more radiation than nuclear energy? It's like the flaws I kept accepting, the excuses I made, the mental gymnastics I performed were all predicated on a lie. A lie that was repeated so often that I and everyone around me believed it.
You've got to stop making excuses for coal. Like your husband, it's toxic to your health and killing the planet.
But why do coal plants cause more radiation than nuclear plants?
You're not gonna like the answer.
Try me.
Government regulations. Nuclear plants have way stricter regulations on how they handle radiation and waste. So it's actually way safer to live next to a nuclear power plant than a coal plant.
Oh, of course. The government regulation. I bet that makes nuclear energy way more expensive than coal because government regulation always drives up the prices and destroys competition on the free market.
Actually, despite these regulations, nuclear is cheaper than coal.
According to professors at the University of Illinois and Ole Miss, while coal costs 2.13 cents per kilowatt hour, nuclear energy only costs 1.82 cents per kilowatt hour.
Coal has more room to explore better options for itself, but really uses it as an excuse to push profit over everything else.
Oh, now I know you're definitely talking about my soon-to-be ex-husband. Cole was such a deceitful piece of work. Do you know how many times he cheated on me? I took him back every time. For the kids, we said. And he was barely around and wasn't even saving for the kids' college fund.
I can see where you're getting this metaphor. Especially since your husband is literally named Cole.
Eris. But that nuclear waste lasts for hundreds of thousands of years. And we could feasibly deal with CO2 in the atmosphere long before we could fix nuclear waste, right?
Actually, there is a way to dramatically reduce nuclear waste. Just not in America. Nuclear waste can be recycled.
But that's just for plutonium. The process is pretty straightforward and can reduce nuclear waste by less than half, while dramatically increasing the usable nuclear fuel.
Okay, well, why isn't this being done already?
Oh, it is. France, Japan, and England all recycle their nuclear waste.
And us? What about America?
Nope. We don't allow plutonium reactors or waste recycling.
Why not?
Jimmy Carter.
Oh, that weak-willed, indecisive little man. You know, his wife was running the whole show because he didn't even want to be president.
More importantly, he let fear decide these policies that have restricted us from making beneficial science-based decisions regarding nuclear energy.
Walk. Jimmy Carter.
Hold on. I thought all you lefty liberals loved Jimmy Carter.
I'm a scientist first. Carter banned recycling nuclear waste in 1977, claiming that it was expensive and could possibly proliferate.
But that reasoning makes sense.
It did in 1977, when there was a huge panic about nuclear proliferation and the technology to recycle waste was still in its infancy.
And Jimmy Carter is an adorable, pure soul who won the Nobel Peace Prize and builds houses for Habitat for Humanity.
But no politicians have overturned this ban, so he's the only one we can blame. Let's think about the argument of proliferation. It is still incredibly difficult, expensive, and impractical to recycle reactor-grade waste into weapons-grade material. And frankly, it would be way simpler, easier, and cheaper to just steal one of our nuclear bombs. The security on those things is atrocious. So proliferation shouldn't really be a concern as far as recycling. And other countries say that with current technology, recycling U-238 into plutonium isn't that expensive.
Then why isn't everyone doing it?
They are, without us. We've been invited to the party, but are too cool to show up. Because here in America, we would rather be ruled by irrational fear and blind nationalism.
Well, this isn't France, England, or Japan. This is America, the greatest country on Earth.
I'm not even gonna touch that. This is a science channel.
And why are we only talking about fission energy?
Instead of splitting atoms apart, why can't we bring them together? Wouldn't that generate less waste? Helium doesn't irradiate anyone. In fact, it's quite fun at parties. And in that chart you showed earlier, doesn't hydrogen fusion release way more energy than fission of plutonium or uranium?
Theoretically, I like where your head is, and I'm incredibly proud of you for retaining that information. Well, we know that fusion bombs are possible, and it would generate way less waste. But fusion in a reactor is really hard to do.
How hard?
Like, cold fusion is the holy grail of engineering hard and incredibly impractical.
But what if you heat things up a little more? Doesn't adding heat and pressure get those protons all excited and increase the possibility for tunneling reactions and nuclear fusion?
Oh, it takes way more heat than could be feasible for budget and energy. The energy spent heating up the protons so a reaction can occur is more than the energy which would be released in the resulting fusion.
I'm not afraid of a little heat, and I'd be willing to put in the energy to make it work.
Good for you? Hold on. Ms. Sharon Noble, are you trying to get out of the lecture by flirting with me?
Depends on if it's working.
I'm not done with the lecture yet.
Oh, come on. I'm already into nuclear fission. Sounds great. Let's shut down every coal mine in the tri-state area and replace them all with reactors. I'll finalize the divorce. Now, untie me.
Your desperation aside, that is what we should be doing.
Wait. You're a lefty liberal, and this is a science channel. Are you even going to bring up renewable energy sources and your love of the Green New Deal?
Wouldn't wind, solar, and geothermal energy sources be way better than fossil fuels and nuclear energy?
Yes, they would, and that's a great end goal. But it's not feasible tomorrow.
Nuclear energy can be used as a transition fuel from fossil fuels to completely renewable energy. Since it produces far less waste, is cheaper, causes less cancerous side effects, takes up less room, and is generally safer, it's a pretty good plan.
Are you saying we need to use nuclear energy as our rebound from fossil fuels before we're emotionally, infrastructurally ready for renewables?
Exactly. Moving entirely to renewables while maintaining our current lifestyles and allowing poorer countries to continue their economic growth will take time to build the proper infrastructure. It's not going to happen in the next few decades. All of those completely renewable by 2035 suggestions on a global scale are laughable to an engineer.
Battery technology will need to be improved. Safe high-voltage power lines will need to be tested, approved, and built. A workforce to build and maintain this new infrastructure will need to be trained.
We already have the physical and regulatory infrastructure for nuclear energy. It isn't the end solution, but it can buy us time and give us the transition we need. Uranium and plutonium only exist in limited quantities and do produce waste, so they're not perfect. But asking the world to just stop using energy while we figure out renewables is eco-fascism and would be horrible for countless economic and human rights reasons.
So if we switch to nuclear energy, we have some time before we need to push for renewable energy? Oh, good. The past 4 years have been exhausting, and I'd really like to relax before marching in the streets again.
Absolutely not. You don't stay with your rebound flame for decades before even looking for the real thing.
We need to transition to nuclear energy now and spend the next couple decades doing everything we can to expand our renewable energy infrastructure. Nuclear energy is a transition fuel, and the sooner we transition away from it, the better.
It's a way to stop the bleeding until we get the patient to a hospital.
So, you're not asking me for commitment, just temporary support before I'm ready to get myself out there again?
Sure.
You know what? Fine. Let's go for it. I think I'm ready for a rebound from coal.
But I haven't even started on nuclear tourism or how plutonium-238 can be the best option for deep space missions.
Did my husband prepay you past the hour?
No.
It doesn't matter. Keep charging at the usual rate. I have his credit card memorized. This will make for excellent payback. Just please stop lecturing and let's get to something with an actual safe word.
If you say so. Time to explore the nuclear option.
Finally. And turn off the camera. We don't want to get demonetized.
Power of math is a curious thing. Make a one man weep, make another man sing. Check your hunch, numbers the right path. Prove what you're feeling, that's the power of math.
Thanks, physics.
Thank you so much for joining us here on Bad Astra. If you enjoyed watching, please like this video, leave a comment telling us what you'd like to see next month, and share it with everyone you know. Be sure to also subscribe and ring that notification bell so you never miss a new episode. And if you can't get enough of me, Eris, and Science Tommy, join our Patreon, where we post behind the scenes, deep dives, and other fun content. A special thank you to all of our Patreon supporters who make these videos possible. Astra out.